I'm Brian Cox. I'm a Professor of Particle Physics at the University of Manchester and the Royal Society Professor for Public Engagement in Science. And amongst other things, I'm the author of several science books, including Black Holes, the Key to Understanding the Universe.
Chapter 1: Black Holes and the Edge of Physics.
Could black holes be the key to a quantum theory of gravity, a deeper theory of how reality, of how space and time works? Well, I think so. It's interesting. These objects, which have been known, I would say, for 40 or 50 years, but theoretically for the best part of a century, have always been fascinating. They're odd things. The simplest way to describe a black hole would be a region of space from which even light can't escape. Predictions that such objects existed go all the way back to the beginnings of relativity back at the turn of the 20th century. But actually, really, I would say into the 1960s, perhaps even into the 1980s, many physicists felt that because of the intellectual challenges that these predicted objects pose, many physicists felt that maybe nature would not create them. I even saw the great physicist Steven Weinberg say that he, in some sense, hopes that these things would not exist because they're so confusing. But we now know that they do exist, and so we have to face the challenges that they pose. Black holes are interesting because, going back to the work of Stephen Hawking in the 1970s, it turns out that they demand that we think about both quantum theory and general relativity together. And the quest to unify those two great pillars of 20th and 21st century physics into what's often referred to as a quantum theory of gravity is in some sense a holy grail for theoretical physicists. But the problem has always been, well, is there anywhere in nature that we can look to observe something that requires us to merge those two theories together? And black holes really are the unique place, as far as we can tell, in nature, where we can see a thing just sitting there in the sky that demands that we consider those two theories working together to hopefully reveal a deeper theory. The idea of black holes goes back a long way, actually, back into the 1780s and 1790s. There were two physicists, mathematicians, natural philosophers, whatever you want to call them, working at the time, that had the same idea, apparently independently of each other. One was a clergyman, an English clergyman called Mitchell, and the other was the great French mathematician Laplace. And they were both thinking in terms of an idea called escape velocity. So the escape velocity is the speed you have to travel to completely escape the gravitational pull of something, a planet or a star. For the Earth, for example, the escape velocity from the surface of the Earth is around 8 miles a second, 11 kilometers a second. If you go bigger, you make a bigger, more massive thing, let's go up to a star, for example, like the Sun, then the escape velocity increases because the gravitational pull at the surface increases. And actually for the Sun, it's somewhere in the region of 400 miles a second. It's really fast. What Mitchell and Laplace thought, and I think it's a very beautiful idea, is they imagined in their mind's eye, well, can you go bigger? Can you imagine more and more massive stars, giant stars, such that the gravitational pull is so large at the surface that the escape velocity exceeds the speed of light? And then you wouldn't be able to see them. There's a wonderful quote, actually, in Laplace's paper, where he says that the largest objects in the universe may go unseen by reason of their magnitude. And this is back in the 1780s or 1790s. So he's imagining stars where the gravitational pull is so vast that even light can't escape and you couldn't see it. Dark stars, I think he referred to them as. Now we know that such objects do not exist in the universe in that sense, in the sense that Mitchell and Laplace meant. But actually, they miss something, which is not surprising because it sounds almost paradoxical. But you can also increase the escape velocity at the surface of an object by squashing it. And it turns out that if you take the Earth and you squash it down and squash it down and squash it down until it's about that big, the radius just less than a centimetre, then the gravitational pull at the surface would be so great that light couldn't escape. And that is essentially the modern concept of a black hole. Now, Mitchell and Laplace's calculations or imaginings were based on Newtonian physics, so pre-Einstein. If we come forward to 1915, Einstein published his general theory of relativity, which is a different model, a better theory of gravity. And it turns out that black holes also exist in general relativity. Now, if we come forward to 1915, Newton's theory of gravity is replaced by a better model, a better theory, which is Einstein's general theory of relativity. But the idea that there can be objects that can be compressed such that they trap light is also present in Einstein's theory. The first physicist to predict such a thing, or at least derive the mathematics that describes such a thing as a black hole, although he didn't know that they existed, was a man called Karl Schwarzschild. What Schwarzschild did was provide an exact solution to Einstein's equations that describes space and time, the distortion of space and time, in the region of a star, or at least an idealized star, which is a perfectly spherical, non-spinning ball of matter. It's a model, a simple model of a star. Now, Schwarzschild described or discovered the solutions to Einstein's equations that describes what happens to space-time outside such a thing way back, actually 1916, just after the theory was published. What Schwarzschild's solution also describes, though, although he didn't think in these terms at the time, was what that space looks like if you completely remove the star, but leave its imprint in the fabric of the universe behind. And that is essentially the theoretical description or the model of a modern relativistic black hole. Now, while Schwarzschild's solution, and by solution I mean we're to picture a distortion in space and time, a distortion in the fabric of the universe. While Schwarzschild's solution does indeed describe the simplest possible black hole that we can model in the universe, people didn't really think in those terms at all until later. You see in the 1930s, Einstein and a colleague of his, Rosen, for example, exploring that space-time and building models of what that space-time might look like. But I think it's true to say that really, certainly until the late 1930s, and actually arguably post-war until the 1960s, most physicists thought that such things would not exist in nature. So they were theoretically interesting, perhaps not practically interesting. The reason is that you have to create such a thing. So it's one thing to have a model of space and time that describes this object called a black hole, from which not even light can escape. But it's another thing for nature to actually make it. So if you go through the 1930s, there's a lot of papers. Actually, Robert Oppenheimer and a student of his, Snyder, wrote a very famous paper just before the war, which explored whether a real star in the universe, at the end of its life, could collapse and collapse without limit to form this geometry, this thing that we call a black hole. Just before the war, Oppenheimer and Snyder showed that under certain assumptions, a star could behave in such a way. But it wasn't really until the work of people like Roger Penrose and Stephen Hawking and several others in the 1960s that it really began to look as if nature would build these things. There's this great quote I remember with some fondness, actually. Arthur Eddington, a colleague of Einstein's, who was very English, very proper physicist. And he said, "Nature will prevent such absurdities from existing." Just, that's it. Nature will prevent it. Well, it turns out nature doesn't prevent it. We now know, and we've observed them, that stars do collapse to form black holes. And then theoretical physics moves on. So people accept that these things should exist, although it's true to say that we haven't actually imaged one until the 21st century. But in any case, people accepted these things should exist. More and more evidence mounted that they do exist at the centres of galaxies and at the sites of collapsed stars. But then we have to face the consequences. What does it mean for our understanding of the universe if there are these objects where space and time behave in a very strange way, where light is trapped, and where it would seem that anything that falls in is at the very least locked away from the universe forever? So to understand the conceptual problems that are faced if these things exist, then it might be worth just describing very briefly the Einsteinian description, the pure description in general relativity. A black hole, what do you see from the outside? Well, there's an event horizon surrounding the black hole. In some sense, it defines the boundary between the external universe and the interior of the black hole. The event horizon is very simply and a bit hand-wavingly, but it's a reasonable description. It's just, if you can imagine a sphere in space, and if you go across the boundary into the interior of this sphere, then even if you can travel as fast as the speed of light, you can't escape. So the event horizon separates the interior of the black hole from the external universe. We'll see a bit later why that's a bit of a hand-wavy description. But another description of the event horizon, which confused people all the way through the history of black hole research, actually, certainly to the early papers in the 1930s and perhaps even post-war, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops. Now that's a direct prediction of Einstein's theory of relativity from the external perspective. If you watched, for example, an astronaut falling in towards a black hole, then from your external perspective, you'd see their time pass more slowly, slower and slower and slower, as the astronaut approached the black hole, until on the horizon you would see their time stop. That suggested to many people in the early days that a star couldn't collapse to form a black hole. It confused them. They thought, well, if a star's collapsing, then does it not freeze forever in some sense on the horizon? So all sorts of initial early conceptual problems, which ultimately were solved. The thing about relativity, just the one sentence thing to understand, is that time can stop from one perspective, but time can pass at the usual rate from another perspective. And indeed, from the perspective of an astronaut falling into a black hole, then for a sufficiently large black hole, like the ones that we find at the centres of galaxies, the astronaut would notice nothing at all as they fell across the horizon into the interior of the black hole. So time passes at 1 second per second on the watch of an astronaut falling in, but from the external perspective, time freezes on the horizon. So black holes are full of these apparent conceptual challenges, which are actually not conceptual challenges at all. They're just a central part of Einstein's general theory of relativity. So that confusion was eventually dealt with and solved, and people understood, certainly by the 1960s, what these things are and how general relativity models them. There is a central problem, though, which is still not solved, which is, you put it this way, what lies at the centre, and I'll be careful with my language, what lies at the centre of a black hole. Now in pure, just in Einstein's general theory of relativity, actually it's not right to talk about the centre of a black hole, really. So what are we picturing? It's this thing called a singularity. You might think of it as an infinitely dense point to which this massive star collapses. It's kind of the natural way to think of it. But actually, just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that the singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. So one way of picturing what's happened when a star collapses to form a black hole is that space and time are so distorted that, in a sense, their roles swap. And so what we thought of as an infinitely dense point, a place in space, at the centre of the collapse of the star, if you like, actually becomes a moment in time and the end of time, the singularity. But the nature of that thing was not and is still not understood. So that's a great mystery. And it's been long accepted that we will need a so-called quantum theory of gravity, a deeper theory of gravity, in order to explain the singularity. And for many, many years, actually, until quite recently, then people thought, well, there we are. We have a problem with the singularity. We don't really have any access to it. We don't have the conceptual tools to explore it. So it may remain a mystery for a century to come. It's not clear what to do. The great revolution in black hole research was to notice, and it began with Stephen Hawking's work in the mid-1970s, was to notice that actually there are conceptual problems at the event horizon of the black hole, not in this extreme place, not only in this extreme place, at the singularity, whatever that might be, but at the horizon. Now that was a real challenge and extremely interesting, because we strongly expect the laws of nature that we understand now, laws of nature that we have full mathematical and conceptual control of, to apply at the event horizon. And so that's why black holes have become so interesting. It's because we have a place where we think, we assume, and indeed we're right to assume, it seems, that we have full control of the physics. We understand what's happening, but there is a fundamental clash of principle between our two basic theories of nature, general relativity and quantum mechanics. And that is ultimately why the event horizon of a black hole and black holes themselves have become so fascinating and so important. The modern revolution in our thought, which is still ongoing, by the way, in understanding black holes and quantum gravity, really does begin with work that Stephen Hawking did in the mid-1970s. Stephen Hawking, in his own words, showed that black holes ain't so black. So we've described them as prisons, in a sense. We're picturing them as a region of space from which nothing can escape. What Stephen Hawking showed in a landmark couple of papers, a tour de force of calculation actually, is that if you consider quantum theory, quantum mechanics, in the vicinity of the horizon of a black hole, then you find that they glow, they produce particles, they have a temperature. This thing that we pictured in Einstein's theory as pure geometry, as just distorted space and time, actually emits particles. It's called Hawking radiation. And one way to picture that, and Stephen in his 1974 paper gives this, he says it's a hand-wavy description. So it's not a full description. You need the mathematics for that. But he gives this hand-wavy description, which is kind of a nice way to picture what's happening. The idea is to imagine, to zoom in on space in the vicinity of the event horizon of a black hole. If you zoom in on any piece of space, the piece of space in front of your nose right now, if you could zoom in and slow time down with a big microscope, you can picture what's happening as a series of particles coming in and out of existence all the time, so-called entangled particles. So it's a picture of what the vacuum of space looks like. Just to emphasize again, it's not a complete picture, it's not supposed to be precise, but it's a reasonable model of what's happening. So particles in and out of existence all the time. And that's happening everywhere, in space, everywhere that you look, in the most empty piece of space you could imagine. That's what's happening. In the vicinity of the horizon of a black hole, you can have the situation where one of those particles, those pairs of particles, is on the inside of the event horizon and one is on the outside. And then it can happen that the one on the outside, instead of merging back with its partner again, can escape into the universe. It's essentially made real by the presence of the black hole. So the other partner is interior to the black hole, and this particle heads off into the universe, removing energy from the black hole as it goes. And this rain of particles, this glow of particles, is called Hawking radiation. That has profound implications. So it's kind of a simple picture of what's happening. But the upshot is, imagine this thing. It's a black hole. It's glowing. It's just space-time geometry, but it's emitting particles, losing energy, therefore it's shrinking, which means that one day it will be gone. So black holes are not eternal prisons. They have a lifetime. One day, whatever's in there is returned to the universe. The question was, the central question that was immediately raised by those calculations is this: what happened to all the stuff that fell in? The way I've described it, the way Einstein's theory describes it, is somehow that stuff goes to the singularity, whatever that thing is, the end of time, a region of space-time that's so convoluted and distorted that we don't understand how to describe it at all. But then, one day, the whole thing is gone. All that's left in the far, far future is Hawking radiation, those particles that were produced in the vicinity of the event horizon. The question is it possible, if you could collect all that radiation, all the Hawking radiation through the whole life of the black hole, is it somehow possible, in principle, that the information about everything that fell into the black hole throughout its history is imprinted in that radiation in the far future? Is that true, or is it not true? You might say, why did I ask that question? Seems like a bit of a random question. It's a very important question. Let's say that I take anything in here, in this room, a book, a table, the camera, right? Anything at all. And I set fire to it. I incinerate it. I destroy it in any way that I can. I could throw it into a furnace. I could put it in the heart of a nuclear bomb and explode it, right? Whatever, just completely incinerate it. In physics, in basic fundamental physics, then it turns out that if you could collect every piece of that thing that I detonated or incinerated, every quantum of radiation, every photon, every particle, everything, in principle, if I could just collect it all, and I was clever enough, then I could reconstruct the thing that I had destroyed. Information is conserved in the universe as far as we know. So every law of nature that we have says that information is conserved. The problem was that Stephen Hawking's initial calculation of the way those black holes evaporate away said that information is not conserved. Said that black holes are erasers of information. To put it very bluntly, the calculation said that once that black hole had gone, then even in principle, there is absolutely no way you could learn anything, reconstruct anything about the things that fell in, including the star that collapsed to form it. So information erasers, the only information erasers that we know of in nature. That was the initial picture of black holes as Stephen Hawking understood them back in the 1970s and 1980s. This became known as the black hole information paradox. So we have a situation, the 1980s, 1990s, 2000s, where it appears that there's a fundamental problem with our understanding of something. Black holes, quantum mechanics, general relativity. When you put them together, you have this apparent prediction that these things erase information from the universe. Some physicists, Stephen Hawking initially actually, felt that that was the case. Maybe these things do erase information. Maybe we don't care about that. Right? Maybe that's the way the quantum theory of gravity is. And other physicists, people like Leonard Susskind initially, for example, George Hooft, the great Nobel Prize-winning particle physicist, and others, felt that, no, there's something wrong with our understanding. There's no way in which we can allow these things to erase information from the universe, thus challenging our understanding of the basic laws of nature. So that debate was vigorous and went on for decade after decade after decade. And the reason it's interesting is because there's a very precise problem posed. So it's not some kind of thing like trying to understand a singularity or understand the Big Bang, or where you can just say, well, we're miles away from understanding. The challenges were posed in a region of space, the vicinity of the event horizon, where we thought we had control of the physics. And so that's really useful because it means that it should be the case that calculations can be performed to resolve. The reason this challenge, this apparent contradiction, this fundamental problem, garnered so much attention is because it occurred, the problem came from physics that everybody thought they understood. So calculating in a region of space under conditions in the universe where we thought and assumed that we had full control of the mathematics of the theories. That's really interesting because it sort of means you have a chance catching a glimpse of some kind of deeper theory by resolving this contradiction. So that's why more and more people got interested in the black hole information paradox. It turns out, if we fast forward to the present day, and a series of papers are still being written, so this is still research that's happening as we speak. But it turns out now that the general view, I would say the generally accepted view, is that black holes do not erase information from the universe. So in principle, if you could collect all that Hawking radiation emitted over eons, right? The lifetimes of some of these black holes, by the way, 10 to the power 120 years plus for some of the big ones. It's one with 120 noughts after it. I mean, the universe is only one with 10 noughts after it years old at the moment, 10 billion years old or so. So we're talking about timescales vastly longer than the current age of the universe. But when they've gone, then in principle, we now think you could collect all that radiation, in principle, put it into some quantum computer, carry out some operations on all that radiation, and reconstruct the information about everything that fell in. But the implications of that, the mechanism by which that happens, I would say it's profoundly exciting because it really does seem to be giving us a glimpse of a deeper theory of gravity. The simple way to say it seems that space and time are not fundamental. So one view, and I emphasize that there are other views, we're at the cutting edge of research now, but one view is a field which has become known as emergent space-time. So what does that mean? It means that space and time themselves are not fundamental. In Einstein's picture, we assume there is such a thing as space-time. This four-dimensional surface, manifold is the technical term, but you assume it. It's part of the model. There are such things as space and time woven together into the fabric of the universe. What they are, Einstein has nothing to say. It seems that there is a deeper theory underlying what we think of as space and time, which is a quantum theory. And so the idea is that space and time themselves emerge from what? From quantum entanglement, from some kind of smaller parts or pieces. We don't know what those things are. We don't know the nature of them. But it does seem that there's a deeper underlying theory from which space and time emerge. That is what we call the quantum theory of gravity. But the key thing to understand is we've been driven to that picture by asking very clearly defined, precise questions about how black holes behave, which goes all the way back to Einstein and then to Stephen Hawking and many others' calculations through the 70s and 80s. Well, supermassive black holes are fascinating things. So these are the black holes that we have images of, radio telescope images. We have two images from a collaboration called the Event Horizon Collaboration. One of a black hole, it was the first one they acquired, of a black hole in a galaxy called M87, which is about 55 million light years away. This is a big galaxy, something like 1 trillion suns. And in the center of that, we've long suspected there was a black hole. Now we have an image of the black hole. It's a black hole that is so supermassive. It's over 6 billion times the mass of our sun. A big black hole by any measure. We also have an image, by the way, of the rather smaller supermassive black hole at the center of the Milky Way galaxy, which is only about just over 4 million times the mass of our sun. So it's a little one, but still big. We think that virtually every galaxy has a supermassive black hole at its heart. Caveat a little bit, because a couple of papers have been released recently suggesting that there may be galaxies observed where there are no supermassive black holes. There are lots of galaxies in the universe. Maybe there are exceptions, but it's fair to say that virtually every galaxy has a black hole at its center. That's an interesting observation because we don't know how those form. One of the reasons is we don't really fully understand how the first galaxies formed in the first place. It's current research, live research. One of the goals of the James Webb Space Telescope is to observe the formation of the first stars and galaxies. It can do that because it can detect very faint, very long wavelength light, which is what you need to detect if you want to look far out into the universe and therefore far back in time towards the origin of the first stars and galaxies. So the JWST, new instrument that's looking at that. There are also a series of new radio telescopes being built. The Square Kilometre Array, for example, in Australia and South Africa, which is a radio telescope array aimed at observing the formation of the first stars and galaxies. So this is live research. It's a fundamental question. How does structure form in the early universe? Not only are black holes interesting from a theoretical perspective, allowing us to peer or uncover deep questions or ask deep questions about the structure of space and time itself, but they're also key to understanding how galaxies form and how structures form in the early universe. How many black holes do we know of? So direct observation, in terms of radio telescopes, we have a direct observation of 2 of them from the Event Horizon Collaboration. The one in our galaxy, the Milky Way, and the one in the galaxy M87. We also have what I would call direct observation of black hole collisions. So this is a completely different technology, a different approach. It's called gravitational wave astronomy. So gravitational waves are ripples in the fabric of the universe. Let's describe them like that. Although I once heard Kip Thorne call them a storm in time, which I think is also a very beautiful idea. And so the idea is that what is a ripple in space and time? They be passing through everywhere now. So through you and me, through the space in which we sit. And they're ripples in space and time. So time speeds up and slows down a bit as these things go through. Distances kind of shrink and expand a little bit as well. So they're real distortions in space and time. And they're caused by, well, actually, pretty much everything that happens in the universe at some level, but they're very, very faint and difficult to detect. The ripples we've been able to detect come from the collisions of black holes or the collisions of neutron stars. So these are highly energetic events in the universe. And the observatory is called LIGO and Virgo. These are essentially laser beams, so-called laser interferometers, about 2.5 miles actually long, 4 kilometers long, at right angles to each other. And they can detect little shifts in the distance between the mirrors between which the laser beams bounce, far, far smaller than the diameter of the nucleus of an atom. So tiny, tiny ripples in the fabric of the universe. By observing those ripples, we can see the collisions of black holes. We tend to see the collisions of big ones, and that's what's called a selection effect. The big ones are more energetic, and so the gravitational waves are easier to detect. But the collisions we're seeing are between black holes that are, for example, around 30 times the mass of our sun. And the number of those collisions is, I think it's fair to say, larger than anyone would have imagined before the observations were made. So it seems there are quite a lot of these black holes floating around that are very massive indeed, 30, 40 times the mass of our sun and upwards. And I think it's fair to say the formation of those things is a mystery as well. It's presumably that they're formed from the collapse of very massive stars, but the number of them, I think it's fair to say, took everybody by surprise. So we've detected, I don't know what the current number is actually, I'm speaking now June 2023, There are collisions being detected reasonably often, but it's tens of collisions, maybe more actually. But it's we have multiple observations of collisions of black holes with black holes, and indeed black holes and neutron stars as well. So it's quite a few. So we're very certain now, as certain as we can be, that these things really exist. As I said, we have images and we have these wonderful observations of the collisions of them. Now, how many black holes might there be out there? There'll be billions of them, billions. So all massive stars that are, 3, 4, 5, 6, 7, 10 times the mass of the sun. There are lots of stars that are above the limit, beyond which we understand that at the end of their lives, when they run out of nuclear fuel, they will collapse without limit. Nothing will stop the gravitational collapse, and they will inexorably form black holes. So black holes are the natural, we used to say, endpoint in the lives of stars above, 3, 4 times the mass of our sun. We now know, of course, that ultimately those black holes will evaporate away again, but, that really is an in principle statement in the far future. So the way to think about black holes is that any star more than, let's say, 3 or 4 times the mass of our sun and upwards will form a black hole when it runs out of nuclear fuel at the end of its life. The numbers are kind of debated, but let's say something like 2 trillion galaxies, large galaxies and smaller galaxies in the observable universe. 2,000 billion galaxies. Pretty much every one of those will have a supermassive black hole at its center as well. So we're talking about, not to steal Carl Sagan's phrase, but billions and billions of black holes. Carl Sagan said, "I never said that." So I'm not stealing Carl Sagan's phrase actually, because he says that he never said billions and billions. Let me give you some glimpses into why black holes are so fascinating and so perplexing and wonderful. So if we go back right to the beginning of the work on black holes in the 1970s, Jacob Bekenstein, a colleague of Stephen Hawking's, actually, one of the first researchers to really begin working on black holes alongside greats like John Wheeler, for example. Bekenstein noticed in a simple calculation, which was initially pretty much a back-of-the-envelope calculation, actually. You notice that you can ask the question, you can answer the question, how much information can a black hole store? That's a strange thing to say, because the model of a black hole is pure geometry, pure space-time. So you might think, well, it's not capable of storing any information. Now, how does something store information? You need some structure, you need atoms or something that can store bits of information. Well, it turns out that you can calculate that a black hole stores information, and how much. This is the fascinating thing. So it stores in bits. The information content is equal to the surface area of the event horizon in square Planck units. What's a Planck unit? It's a fundamental distance in the universe that you can calculate by putting together things like the strength of gravity, Planck's constant, the speed of light. It's the smallest distance, often described as the smallest distance that we can talk about sensibly in physics as we understand it, the Planck length. This is a bizarre result. There's so many things that are bizarre about that. The questions it raises. What's storing the information? How is information stored? Why is the information content of a region of space equal to, or why does it have anything at all to do with the surface area surrounding that region rather than the volume? If I asked you, how much information can you store in your room, the room that you're sitting in now, just say it's a library, then you would say, well, it's to do with how many books I can fit in the room, or hard drives, or whatever it is, right? It's to do with the volume of the room, the space. But black holes seem to be telling us that there's something about the surface surrounding a region which is fundamental. This is the first glimpse, I think, of an idea called holography, which now seems to be correct in a sense. So holography What is that? It's the idea that there are different descriptions of our reality. There's one description which is the description that we're all comfortable with and familiar with, I would say, which is that we live in this space, the 3 dimensions of space, and time is a thing that ticks. And Einstein told us that they're kind of mixed up, but still you have this picture of space being this, right, the thing in which we exist. There's an equivalent description, it seems. It's been proved, by the way, for a very specific model called ADS-CFT by a physicist called Maldacena. There's an equivalent description which is of a theory that lives purely on the boundary of the space. And it's absolutely equivalent. It's an absolute perfect description, a dual theory of the description of the space itself in the interior of this region. That's called holography because that's, if you think about what a hologram is, then at the very simplest level, it's a piece of film. But that piece of film contains all the information to make a 3-dimensional image. So all the information about a 3-dimensional image is contained on a 2-dimensional piece of film. It's basically a hologram. And it seems, from our study of black holes, and the hints go all the way back to the 1970s to Jacob Bekenstein's work, that our universe is like that in a way that's not fully understood yet. The picture is that, and physicists, I always like to joke, when they don't really know or the language isn't present, then physicists often say, in some sense, and wave their hands. So in some sense, there's an equivalent description of our reality, which lives on a boundary surrounding it, perfectly equivalent. And you might ask the question, well, what's the real description of reality? And the answer is we don't know, but they're equivalent. So it's strongly suggestive that there's let me say a deeper theory, but at least a difference theory of our experience of the world, of space and time, that does not have space and time in it. And that's one of the wonderful surprises that's really emerged from, at least in part, from the study of black holes and the attempt to answer the very well-posed questions that black holes pose. I should say that the work done by Maldacena, the ADS-CFT correspondence, was purely mathematical. So it wasn't framed in the study of black holes, although the questions ultimately seem to be intimately related. So that's number one. So the study of black holes seems to be strongly suggesting that these ideas of holography, holographic universe, which came from a different region of physics, actually, from trying to understand other things, those descriptions may be valid, may be useful, may be in some sense true. The other remarkable thing for me, I think, in the study of black holes, is an intimate relationship between black hole physics and quantum computing. This was wholly unexpected, I think it's fair to say. The relationship comes by saying, okay, so there's a theory on a boundary, a quantum theory, which is a perfect description, a dual description of the physics of the interior of a region of space. You might say then, well, how is information encoded on this boundary? How does that relate to the physics of the interior, space and time? And it seems that we're beginning to glimpse an answer, at least in very simplified models. And it seems that the information is stored on the boundary redundantly, which means that you can lose a bit of it and still fully specify the physics of the interior. Redundant storage of information. Now, if we go to quantum computers, there's an engineering challenge in building quantum computers. And just to emphasize, we have these things. They're not theoretical, they exist in labs across the world. There's a challenge, which is how to store information in the memory of the quantum computer safely, robustly, because quantum computer memory is notoriously susceptible to any interference from the outside environment. If any of the environment in which the memory sits interacts with the memory in any way, then the information is destroyed. So it's a tremendous challenge. And there are deep problems associated with the fact that you can't copy information in quantum mechanics. which is basically the way that your iPhone or whatever it is stores information and prevents errors entering into the memory of the computers that we're all familiar with. It's basically copying information. You can't do that in quantum mechanics. Fundamental. It's called the no cloning theorem. Engineers have had to develop very clever algorithms and ways of trying to store information in quantum computer memory and build the memory such that it's resilient to errors. And it turns out that the solutions that are being proposed and explored look like the solutions that nature itself uses in building space and time from the theory, the quantum theory that lives on the boundary. It's really strange. And I just emphasize, you're not meant to understand what I've just said, because I don't understand what I've just said, because nobody understands what I've just said, right? We're catching glimpses of this theory, and that's where the research is at the moment. It's why it's tremendously exciting. There's papers being published all the time that are digging more deeply. They're suggesting pictures of reality, physical pictures of what's happening, but there's no sense, and I emphasize it, in which everybody agrees on these pictures. So I'm giving you an interpretation, and there will be other people who have different interpretations. But it does seem that whatever this quantum theory is that underlies our reality, then there's some redundancy in the way the information is stored in that quantum theory. And it does seem that that's akin to or similar to the way that we will in the future encode information in the memory of quantum computers to protect them from errors, called a quantum error correction code in the jargon. I find that fascinating. It's tantalizing. It's a glimpse of something Einstein said. There's a beautiful phrase, which actually the physicist Sean Carroll used as a title of one of his books on this. Einstein said that if you look at nature really carefully, and keep pulling at the intellectual threads and keep going and just keep delving down into what nature seems to be trying to tell us, then if you're lucky and persistent, you can catch a glimpse of something deeply hidden. It's beautiful, that, isn't it? A glimpse of something deeply hidden, which is the deep underlying structure of nature. And it does seem that we're beginning to glimpse something deeply hidden. From the study of black holes, the related, surprisingly, field of quantum computing and quantum information, we're glimpsing something deeply hidden, the deep underlying structure of reality itself. And I think it's very beautiful. No one really knows, I think it's fair to say, where this is going, but they're hints of something deeply hidden. Black holes may well help us understand a different but related question, which is what happened at the beginning of the universe. So I think black holes are, at the moment, the most interesting naturally occurring objects, in the sense that they're helping us understand, or forcing us into a deeper understanding of what space and time are. And my view is that if we're going to talk about the origin of the universe, even ask questions such as, did the universe have a beginning in time, which we don't know the answer to, then it surely seems to me that we have to understand what space and time are before we can ask and have any chance of answering such questions. And black holes, it turns out, are the objects that we can see, that we can observe, that actually exist in nature, that force us down that route to ask questions, sharp, well-defined questions, actually, about the nature of space and time themselves. It surely must be the case that as we get a deeper understanding of what let's call it the fabric of the universe is, then we can begin to get a rather deeper understanding or more insight into questions about the origin of the universe itself, should it have one. I mean, why do I keep saying should it have one, by the way? Because you might be watching this saying, well, it's a Big Bang. We know there's a Big Bang, and that's true. We do know there was a thing called the Big Bang. What do we mean by that, though? We mean that 13.8 billion years ago, the universe was very hot and very dense everywhere. The region of space that now forms the room in which you sit was very hot and very dense 13.8 billion years ago. We know that all the galaxies are receding from each other at the moment, and just put very simply, if we make the measurements of how they're receding and run time backwards, then you find that they're all on top of each other 13.8 billion years ago. So we know something interesting happened back then. We have a measurement to it. It's not up for debate. Often when people say, well, how do you know about this Big Bang thing? The vast amount of evidence that such a thing happened, the best evidence probably is you can see it. So we see something called the cosmic microwave background radiation, which is the universe as it was about 380,000 years after the Big Bang. What we see there, we have a photograph of it, is a universe that was very different from the one we see today. There were no stars, no planets, no galaxies. It's just a hot, glowing mass of gas, primarily hydrogen and helium, and we have a photograph of that. So we know something interesting happened. But do we know that that was the origin of the universe? No, we don't. We have theories, strong physical pictures of the universe before the Big Bang, in a very precise sense, before the universe was hot and dense. Theories called inflation, which say that space was still there and it was expanding very fast. And then that fast expansion drew to a close, and all the energy driving that expansion got dumped into space, made particles, and that's what we call the Big Bang, the so-called hot Big Bang, as we term it today. What happened to start inflation off? The answer is we don't know. When did inflation start? We don't know. We have a minimum time that it needed to go on for, but we don't know what or even if that phase of the universe constitutes a beginning. There are so many reasons to study black holes. There's fascinating, beautiful things that we know to exist in the universe, pose fundamental questions. But one of the reasons that we're really interested in them is that, put it this way, there's singularities at the end of time. Right? The Einstein description says that inside a black hole there's a singularity, and locally, at least in that region of the universe, that constitutes the end of time. There's a singularity, maybe, at the beginning of time, the other end of time, if you like, that we're also interested in. You might call it the Big Bang singularity, the origin of the universe. And it seems to me to understand that singularity at the beginning of time, the Big Bang singularity, then we need to understand the singularities at the end of time. And the great benefit is we can see those. So we can watch them bump into each other. We can see them at the centers of galaxies. We can make observations of them, and we can do calculations. Understanding black holes, I think, will be the key to a deeper theory of our universe. So in that sense, I think it is fair to say that black holes are the keys to understanding the universe.
Chapter 2, Alien Life and the Fermi Paradox.
Enrico Fermi is one of the great physicists, legendary Italian physicist, who laid many of the foundations of modern 20th century physics, so-called Fermi-Dirac statistics and all sorts of things. If you do a degree in physics, then you will spend a lot of time revising equations and theories that Fermi did. One of the great legends. The Fermi paradox is it's probably the thing he spent least time on, actually. It's almost one throwaway remark that he delivered. And the question is, where are they? By they, I mean aliens. The heart of the Fermi paradox is this. We know that we live in a big old galaxy, in a big old universe. And let's, for the purposes of this discussion, confine ourselves to the Milky Way galaxy. The Milky Way galaxy, we now know, has something like 400 billion suns. And we now know that most of those suns have planetary systems around them. So trillions of planets. The galaxy's been around for pretty much the age of the universe, 10 billion years plus. And so there's a lot of real estate, and there's been plenty of time for civilizations to develop in the galaxy. The Fermi paradox at its heart is the statement that, notwithstanding the fact that there have been billions of years on billions of worlds for civilizations to arise, we see no evidence of any of them in the galaxy at all. So the paradox is why? It's a paradox. And I think it's a very good question. It's an extremely good question. And there can be many answers. And the great fun, or the great, I would say the intellectual value of the Fermi paradox. So if we accept that we haven't seen any, so let's accept that. Let's accept that there isn't a UFO sat in some warehouse in Roswell or something like that. Let's accept that we haven't seen any. Let's accept, well, we have to accept the picture that I've just given you about the Milky Way galaxy and its age, because that's a measurement, so we know that. The question is then, why? How do we resolve these apparent contradictions and paradoxes? So one answer to the Fermi paradox, is the idea that we don't seem to see anyone, is that no one ever evolved. Right? So life didn't get complex. Why might we think that? Well, what did we need to produce our civilization on this planet? Well, on this planet, one thing we needed was time. We have good evidence that life was present on this planet 3.8 billion years ago, perhaps even earlier. The planet is 4.5 billion years old. So we know, as a matter of fact, as an observation on this planet, that life was present 3.8 billion years ago, but it took 3.8 billion years, give or take a few tens of thousands of years, to go from the origin of life to a civilization. Let's say from cell to civilization. 4 billion years. That's 1/3 of the age of the universe. So a possible answer to the Fermi paradox, the question of why there are no civilizations, is because the Earth is pretty much unique in the Milky Way galaxy, in that it was stable enough, the climate, the conditions on Earth were stable enough for long enough for life to go from cell to civilization. If you think about it, that's a big ask. What I'm saying is, on this planet, an unbroken chain of life existed for almost 4 billion years, notwithstanding the fact that we live in a violent universe. The sun must have been stable enough for long enough. We know the output of the sun has changed over those billions of years, but it's not changed so radically that it managed to erase, destroy life on Earth. We know that we live in a violent universe. We know there are supernova explosions all over the place. It turns out that there have been no stars massive enough to explode as a supernova in a way that would damage life on Earth or erase life on Earth in this vicinity for 4 billion years. We know that nothing has happened. We know that there have been impacts on the Earth, right? We know that the famous impact that wiped out the large dinosaurs, there's been no impact big enough to destroy the unbroken chain or break the unbroken chain of life for 4 billion years. So maybe it's the case that whilst there are billions of planets which may have liquid water on the surface, may have oceans that can support life, it may be that none of those planets in the Milky Way galaxy have been stable enough for long enough to produce a civilization. So that would be a property of the planet itself, the so-called rare Earth hypothesis. Actually, I should say it's a property of a solar system. It's not really just a property of the planet. It's a property of the parent star. You could ask the question, well, if it was a binary system, for example, a binary star system, many stars are binary star systems. Is it possible to have a planet with a stable climate, stable enough orbit in a binary star system to support an unbroken chain of life for 4 billion years? Perhaps not. When we talk about rare Earth, I think I would like to talk about rare solar system. Another possibility with the Fermi paradox is that it's not a paradox, they are here. So there are intelligent civilizations out there and they are present in the solar system. It's possible. Let's think, for example, what such an intelligence might look like. Well, who knows? They could have sent nano machines to our solar system. There could be probes all over the place in the solar system, but if they're the size of an iPhone, then we'd have no way of detecting them. So it could be the technology of a sufficiently advanced alien species, a civilization, is so beyond anything we can comprehend or detect that we haven't seen it and we've been fooled into thinking that there are no advanced civilizations in the galaxy. And that's certainly entirely possible. Another possibility, another possible resolution to the Fermi paradox is just that the galaxy is so big. The distances between stars are so great that if you imagine there's another civilization, let's say on the other side of our galaxy, let's say 20 million, 30 million, 40 million light years away, even if they had the most powerful radio transmitters you could imagine, or even if they'd spread out to neighboring solar systems, then it may just be that the distances are so great that the signals are diluted, that we can't detect them because they're too weak, or that it's just very, very, very difficult in an engineering sense to build interstellar spacecraft. Now, perhaps you can build a spacecraft that can hop a few light years away to the nearby solar system, 4 light years in our case to Alpha Centauri, but you can't build spacecraft that can traverse a galaxy. That's a possibility. One of the arguments against that for me is the argument, it's called the space travel argument against the existence of extraterrestrial life. And it's often framed in terms of self-replicating machines, so-called von Neumann machines. So imagine it's possible for us, for a civilization, to build a machine, some kind of AI, that's sufficiently smart and capable that it can fly to a nearby solar system, reproduce itself, copy itself, and then send the copy out to the next solar system, and so on. So you have, if you build a one successful replicator, you have an exponentiation of replicators. You have 1, and then 2, and then 4, and then 8, and so on, exponential growth. And you can show that even given our rocketry technology, you can cover a galaxy like the Milky Way in a reasonably short space of time. By reasonably short, I might even mean 100 million years, right? That's reasonably short on galactic timescales. But the key point is once a single successful replicator has been launched, then it is inevitable that over a few tens of millions of years, the galaxy will be covered with replicators, and we don't see any evidence of them. It's possible that we can infer that if we assume that we could detect them, then the absence of them may allow us to infer that no civilization has ever got to that point. And I think that's quite a persuasive argument. Now, it's possible that there are many civilizations out there, but the advanced civilizations choose to remain hidden. Sometimes called the dark forest hypothesis, the quarantine hypothesis. We've been asked to make moral judgments or judgments on how a civilization will behave, what they will choose to do. And that's, of course, impossible to judge. But let's imagine civilizations, when they get technologically advanced, also get intellectually and morally advanced. And let's say that they choose, perhaps for good reason, let's say they choose to remain hidden because they don't want to draw attention to themselves. Let's say it's inevitable that if you think about it carefully and you think there are other advanced civilizations out there, then you choose to remain silent. You hide yourself as best you can. It's possible that that's the way that a civilization would think. Maybe that's a logical thing to do. I find it difficult to believe, given human history, that that's the way that intelligent civilizations behave. We certainly haven't made any attempt to remain hidden so far. We've broadcast radio signals out to the stars, the Arecibo message, for example, albeit weak ones. We've launched on our space probes, like Voyager, maps, pulsar maps in that case, which shows the location of our solar system should any other civilization find it. So at least at the moment, we haven't come to the view, which may be a wise view, but we haven't got there, that we should remain silent. Quite the opposite. We've tried at every opportunity to broadcast our existence. Maybe that's because Carl Sagan argued, I think, that a sufficiently advanced civilization, a civilization that can build interstellar spacecraft and communicate across interstellar distances, perhaps is wise enough to have overcome those primitive instincts, the instinct to cause trouble, to fight wars, to colonize, to walk over other civilizations. Perhaps it's inevitable that with technological advance ultimately comes wisdom. But it's a hypothesis. Maybe it is. Maybe it's just anybody sufficiently clever to build an interstellar spaceship will be also sufficiently clever to hide it and not draw attention to themselves. Maybe it's immoral. Maybe it's like Star Trek. Maybe it's the prime directive. Maybe it's morally certain that if you're sufficiently advanced, you decide to take the position that you will never introduce yourself or interfere with another civilization. Maybe that becomes a kind of law of nature for sufficiently intelligent beings. Maybe that's conceivable as well. Another explanation for the Fermi paradox might be that civilizations live and die. They rise and then they fall. And because of the sheer timescales involved and the sheer size of the galaxy, no two civilizations ever overlap. I once had the great pleasure of meeting Frank Drake, the Drake equation, a legend, in his house. And he also grows orchids. And I arrived at his house just coincidentally on the day that this rare orchid flowers. And it flowers for, I think, 1 or 2 days and then goes away again for the year and then flowers again the next year for 1 or 2 days. And he used it as an analogy. He said, well, maybe civilizations are like that. So maybe civilizations are like rare orchids, and so they flower and die and flower and die. And just because of the sheer timescales involved, none of them ever overlap. And so there could be the wreckage, the ashes, the fossils of civilizations out there. But of course, we would have no way of knowing until we explore the galaxy and maybe find the ruins of these other civilizations. Who knows? I mean, it's quite plausible if you think about it. Are we going to exist in 10,000 years' time? It's to a large extent in our hands. Maybe we're sufficiently stupid that we won't exist beyond the next century. There's an idea in this field, trying to explain the Fermi paradox, called the great filter. Now, the great filter can lie in our future or our past. So let's think about what it would mean for a great filter to lie in our future. That would mean that civilizations do arise in the Milky Way galaxy and get to somewhere like the position that we're at now. So they develop rocketry, they develop nuclear power, nuclear weapons, for example, they industrialize, but then there's a filter in the future that stops them becoming true spacefaring civilizations. So stops them becoming multiplanetary species and stops them ultimately traveling between solar systems to begin to colonize a galaxy. So why might that be? Why might there be a filter waiting for us in our not too distant future that's going to stop us going on to Mars and stop us escaping our solar system? What might stop us from becoming an interplanetary species and ultimately traveling out beyond our solar system? I don't think it's technology. As far as I can see, I don't see anything in the laws of nature in principle that would stop us from becoming an interstellar species. It might be 1,000 years in the future, 10,000 years in the future, might be 100,000 years in the future. Even that, right, 100,000 years, it's a blink of an eye in the lifetime of the universe, in the lifetime of a galaxy. So I don't see any reason in principle why we couldn't become an interplanetary, interstellar species other than potentially our own stupidity. And I think that probably it could be one of the reasons why we don't see any other civilizations around. It could be that our knowledge, our scientific prowess exceeds our wisdom, exceeds our political skill. It could be that once a civilization develops the means to destroy itself in the form, for example, of nuclear weapons or biological weapons, or maybe some kind of a lack of control of AI, who knows? It may be that once a civilization acquires that technical know-how, then it goes ahead and destroys itself essentially inexorably, because it's just too difficult politically to run a civilization that has the power to destroy itself. If you look back through our recent history, there have been several occasions that we know about, that I know about, and you know about, where we came very close to destroying ourselves, or at least setting us back to the Stone Age, basically. The Cuban Missile Crisis, well-documented events in the 1980s, for example, where there could have been nuclear launches and weren't. And I'm sure there are many others that we don't know about. There's the challenge of climate change. We're completely incapable of coming together at the moment as a global civilization to address that challenge. That could set our civilization back. Biological weapons, the threat of AI, we seem to be completely incapable of regulating those threats. So it might just be almost a law of nature. Things like us, right? Things that can build an industrial civilization are just inherently too stupid to get out there to the stars. And I wouldn't put that past us. My favourite's the other one, so I'll do the other great filter. If I was to guess, and this is a guess, right? If I was to guess why we see no evidence of other civilizations out there, the so-called great silence is what astronomers call it, is because there aren't any, and there never have been any. That's my guess. The reason I guess that, and I emphasize it's a guess, is biology. So if you look at the history of life on Earth, then we see that life began 3.8 billion years ago, let's say. But then we see for the best part of 3 billion years on this planet that there's nothing more complex than a single cell. 3 billion years. It's only in the last billion years or so, perhaps a little bit less, that multicellular life has existed on this planet. And there could be good biological reasons for that. One that springs to mind is the evolution of what's called the eukaryotic cell, which is the cell with the cell nucleus and all little organelles and chloroplasts in plants and all those things, which form all multicellular living things on the planet. Those cells, which seem to be prerequisite for complex multicellular life, evolved once on this planet, as far as we can tell. It's pretty widely accepted. It's called the fateful encounter hypothesis. And so it seems that there was a very unusual evolutionary event at some point, maybe a billion and a half, even 2 billion years ago, that laid the foundations for us. If that's typical, if it typically is the case that it takes 4 billion years from cell to civilization, then I think there may be very few planets in a typical galaxy which are stable enough for long enough for that process to proceed. And we could be, for all we know, on the fortunate end of evolutionary timescales. We don't know. Let's imagine that actually we were on the lucky side, and really, on a typical planet, if there is such a thing, then it takes 3 or 4 times as long. That would exceed the current age of the universe. My guess is that whilst I think there might be microbes all over the place, I wouldn't be surprised, I'd be delighted, but I wouldn't be surprised if we found evidence of microbes on Mars, Europa, Enceladus, even in the subsurface oceans of places potentially even as far out as Pluto, right, in subsurface lakes, if they exist, liquid water below the surface, who knows? I wouldn't be surprised if we find microbes all over the place. But a galaxy full of complex living things, other planets with not only complex life, but sentient life, things as smart as us, things smart enough to build rockets and head out to the stars. My guess is that a typical galaxy may have less than, on average, less than 1 civilization per galaxy. Let's put it that way. But actually, just to say, there's a very famous book I'd strongly recommend, Barrow and Tipler, called The Anthropic Cosmological Principle. It's a great book, one of the books I grew up with. And in that book, Barrow and Tipler say that in their view, there might be 1 civilization in the observable universe, which should be us, right? So who knows whether we should go that far. But I think civilizations are very rare. And I think it's the biology. So I'm guessing, I'm giving you a guess. I'm saying that in my opinion, I think there's 1 civilization in the Milky Way galaxy, and there only has ever been 1, and there might only ever be 1, and that's us. Which, by the way, means that we have a tremendous responsibility not to mess this up. Because as I said I was asked to give a video introduction to the climate summit, the COP26 climate summit in Glasgow recently. Give the world leaders 1 minute. They said, you've got a video, say something to them. And I said, I think, let's assume that we're the only civilization currently in the Milky Way galaxy, perhaps the only civilization there will ever be. That means the Earth is the only island of meaning in a sea of 400 billion suns. And so if we destroy this, we might destroy meaning in a galaxy forever. Discuss. So That's my guess. However, that's a hypothesis. I will be delighted if it turns out that's not true. And that's not just because it removes some responsibility from me and you and everybody else to preserve intelligence in a galaxy of 400 billion suns, as the weight of responsibility is heavy, but also every scientist should be delighted if they are shown to be wrong. Because the moment you're shown to be wrong, it means you've learned something, and that's the way that knowledge progresses. So nobody should be worried about making a guess, advancing a hypothesis, an educated guess, or even an uneducated guess. Don't worry about doing that. As long as the moment it turns out you're wrong, and me being wrong, by the way, would constitute a flying saucer landing and some aliens coming out like E.T. and saying hello, so that would be brilliant. But it would be doubly brilliant because it would turn out that I'd learned something about the universe, which is that complex civilizations are not as rare as I think they are, or civilizations aren't as rare. So that would be a good thing. So there's a lesson. I think the biggest questions are in physics, how does space and time emerge from a deeper theory, if indeed space and time emerge from a deeper theory? I want to know what time is, and I want to know what space is. I want to know how likely it is that life begins on a planet that has the potential to support it. So I think a deep question is the question of the origin of life. How does a planet, which is geologically active but devoid of biology, become a planet that it has biology on it? What is the transition from geochemistry to biochemistry? How does that happen? How likely is it? I want to know how likely it is that given microbes on a planet, those microbes will get together into complex multicellular things. I want to know how something as complex as the human brain evolves in the universe. How common are brains in the universe? I'd like to know what it is. How does this little blob of matter, which is just a pattern of atoms, it's just a temporary pattern of atoms, how does that give rise to the feeling of existence, the feeling of consciousness? It's often called a hard problem in neuroscience, and it's a very hard problem. So I want to know the origin and nature of consciousness. I want to know whether it is possible for a computer to be conscious, not only to pass the Turing test, but actually to be conscious. What do I mean by that question? My guess is that it is possible, but I don't know. I want to know whether the universe has a beginning in time or whether it's eternal. I want to know what the origin of the laws of nature is. Why is gravity so much weaker than all the other three forces of nature? Why does the Higgs field produce masses for top quarks and up quarks and down quarks, but not photons? I mean, I know the answer to the question. It doesn't interact with photons, but why? Right? What's the origin of those laws of nature? Is there only one way the universe can be? Is there only one logical construct for a universe, and it's this one? Or are there other possible universes? Do other possible universes exist? Is it possible that you can have universes which do not support life? Is it possible? How rare are universes that have laws of nature that can support living things? I could go on.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.